Hey guys, and welcome back. Today we're looking at algebraic solutions to simultaneous equations by using the equating method. If you joined me for our previous lesson on solving simultaneous equations either by elimination by subtraction, elimination by addition, or multiplication and subtraction, that probably gave you a good understanding of what simultaneous equations are and practiced your algebra skills, which will be helpful here. However, we're also going to look at solving nonlinear simultaneous equations. And the type of equation does affect the type of methods we'll use in order to solve it. The equating method can be used for both linear simultaneous equations and nonlinear simultaneous equations. My name is Ms. Danielson, and let's get started so I can show you what I mean. Although we're not going to be doing any graphing today, it would help if you saw the graphs of different types of equations just so you could understand what I mean by linear and nonlinear. Linear equations can only contain number terms and x terms. No x squares, no x cubes. For example, the equation for a horizontal line is just y equals some number. For a vertical line, it's just x equals some number. For a positively sloping line, we have y equals some positive number of x plus some number. And for negative sloping lines, we got y equals some negative number of x plus some number. When it comes to curved graphs, the first ones that come to mind are probably positive quadratics. These perfectly symmetrical, smooth curves that have a parabolic shape that looks a bit like a happy face. For these types of equations, the x squared term is the most definitive term. These equations always have some term, which is some number of x squared. Then they may or may not have some number of x and some number. For a positive quadratic, the most important feature is that we've got a positive number of x squares. For a negative quadratic, we've got some negative number of x squares. You might also be familiar with cubic equations, where their defining feature is an x cubed term. Those graphs look a bit like this. For positive cubics, they start low, they rise up to a maximum, and then it dips back down to a minimum, and then they rise again up to some infinite value above. This is a positive cubic because it has some positive number of x cubed. We've got positive cubics which start low and end high, and we've got negative cubics which start high and end low. And again, the defining feature in the equation is that the x cubed term has a negative coefficient. Apart from cubics and quadratics, there are also reciprocal equations, which you should be somewhat familiar with, although they're much more difficult for you to graph. Reciprocals involve some kind of division by some variable. So for example, y equals any expression, any calculation over any expression that involves x. So long as this fraction can't be simplified in such a way that the x is taken out of the denominator, this will have a reciprocal shape. The common reciprocal curves you might have seen before are ones like this one, y equals 1 over x, or y equals negative 1 over x. We could also have some very interesting looking reciprocals like this one here. Again, it's any expression divided by some expression involving x. And look at the shape of this curve. It's got 3 different parts to the curve. But this graph is all thanks to just one equation. The reason our reciprocal curves all look so strange is because they all have asymptotes. And the reason for that is because we can't divide by 0. So in every single case, you should notice that there's a line that the curve never reaches or crosses, although it seems like it's getting close. And the reason for that is that we cannot divide by 0. So on this curve, you should see that x cannot be equal to 0. On this curve, you should see that x cannot be equal to 0. And on this curve, you should see that the denominator can't be equal to 0, in which case this could not be equal to 1, because x squared would be 1 and 1 minus 1 would be 0. Or negative 1, because negative 1 squared would be 1 and 1 minus 1 would be 0. We can't divide by 0. Now, like I said, today we're not going to be graphing, but it might be helpful to see the types of equations that you're trying to solve, particularly when they're not linear equations. For the most part, at higher GCSE, any equation which is not a linear equation, which you're asked to be solved, you should generally be able to convert it into a quadratic form and solve that quadratic. So I hope you joined us for our previous lesson on solving 3-term quadratics, 2-term quadratics, completing the square, and the quadratic formula, because those are our methods for solving quadratics. As a nice, easy introduction to our equating method for solving simultaneous equations, let's have a look at this linear example. As you can see, I've got 2 linear equations. If I were to graph them, they would look like this. And I'm hoping you could tell by the equations which one is which. The red line is clearly a downward sloping line, so it's a line with a negative gradient. That must be this one here. That means that this point where that red line crosses the y-axis must be our y-intercept positive 9. The blue line has an upwards sloping gradient, so that must be this equation here. My gradient must be positive 1, because that's the number of x's I've got. And this y-intercept here, where it crosses the y-axis, must be the negative 7. As I said before, in this lesson we won't be graphing in order to solve. The graphs help you to see where the answers come from. We're looking for an x value and y value that satisfy both of these equations simultaneously at the same time. So it's an xy value or a coordinate that's on this red line, but at the same time it's also on this blue line. So it's this point right here. That's the only combination of x and y values that lies on both lines. But to solve this algebraically, let's follow these steps. Step 1. When the equations are both in the format where the same variable is the subject, usually y is the subject, and that's the case that we have here. Y equals some expression in x. Y equals some expression in x. We can then set the equations equal to each other because both of these equations are equal to y, and we're looking for that common y value for both equations. So for equation 1, y is equal to negative 3x plus 9. For equation 2, y is equal to x minus 7. So negative 3x plus 9 must be equal to x minus 7. Step 2. Now that I have just one equation, and that one equation just has one variable, we're forgetting about the y variables for now. We can solve this one equation, which has got x variables on both sides of the equation, the same way we would solve any linear equation. Get your x's together, get your numbers to the other side, get your x on its own, and see what it's equal to. So first we'll move our x's to the same side. I've moved my negative 3x over to the right-hand side, making it positive 3x, and I moved my negative 7 over to the other side, making it positive 7. So I've got 9 plus 7 equals x plus 3x. I can simplify that. 9 plus 7 is 16. X plus 3x is 4x. Now I want the x on its own though, so I'll get rid of that 4, which is multiplying by the x. The opposite of multiply is divide. So x must be equal to 4. Step 3, once you know the value of one of the variables, use either of the original equations to work out the value of the other variable. So it's my choice. I'm looking at the two equations, and I'm thinking equation 2 looks quite a bit simpler. Y equals x minus 7, if x is equal to 4, becomes y equals 4 minus 7, which is simply negative 3. So it was as simple as that. X is equal to 4 and y is equal to negative 3. And my step 4 is simply to make that clear. Finally, step 5 is just to check that your answer works for the other original equation. Remember, we're looking for an x and y value that work for both equations. I already know it works for equation 2, so let's try for equation 1, which was y equals negative 3x plus 9. Now that I know that y is negative 3 and x is 4, I can check if negative 3 is equal to negative 3 times 4 plus 9. Now doing this mentally, I know that negative 3 times 4 is negative 12, and negative 12 plus 9 is negative 3. So yes, I'm pretty confident that my answer is correct. X is equal to 4 and y is equal to negative 3. Please take a minute now to copy down that example and those steps, because we're going to use those same steps to work out nonlinear simultaneous equations. These simultaneous equations are clearly not linear. Because of their x squared term, they are both positive parabolas. And as you can see, just like our linear equations, my positive parabolas do cross at some point. This one looks like it's going to have just one solution, but remember that parabolas, because of their curve, could have as many as 2 solutions. So let's go through those steps again. Step 1, when the equations are both in the format where the same variable is the subject, so I've got y equals x squared plus 3, and I've got y equals x squared minus 9x plus 16, we can set these equations equal to each other. Step 2, we now just have one equation, and that single equation only has the variable x in it. There's no more y's. So let's try and solve this equation. Now it may look difficult at the moment because it's got x squared terms in it, but let's start by getting those x squared terms to the same side. Here I've taken the x squared term from the right side over to the left side. It was positive, so I've minused it. And look what happens. X squared minus x squared, it's disappeared. I no longer have quadratic to solve, I just have a linear equation. So don't panic as soon as you see that x squared. That doesn't necessarily mean this is going to be a quadratic that we need to solve. Remember our graph? It looked like it crossed in only one place. Well, now we have a linear equation to solve, and we know linear equations only have one possible solution. So, solving this linear equation, rearranging to get x on its own. First I subtract the 16 across. And then to get the x on its own, it's being multiplied by negative 9. So let's divide by that negative 9. Note that I didn't change the negative 9 to positive 9 because I'm not changing from a subtraction to an addition. The operation I'm changing is from multiplication to division. But I was multiplying by negative 9, so I will now divide by negative 9. I'm not changing the number, just the operation. Now this is going to be a decimal value, so I'd rather leave it as a fraction to help me find an accurate value for what y is. So negative 13 over negative 9, a negative divided by a negative is definitely going to be positive. So now let's just think how many 9s go into 13. There's 1 9 in 13 with 4 left over. So the remainder 4 remains over the denominator of 9, 1 and 4 9ths. So step 3, once I know the value of one of the variables, let's use it in either of the original equations to work out the value of the other variable. Looking at my two equations right now, I think you'll agree, equation 1 seems to be a little bit simpler. So I've substituted my value for x into equation number 1, and I find it's a lot easier to work with top-heavy fractions than it is with mixed numbers. So I left this as 13 over 9. So 13 over 9 squared plus 3. When you square a fraction, we square both the top and the bottom. 13 squared is 169, 9 squared is 81. So 169 over 81 plus 3. Again, I've got a top-heavy fraction. Think of how many 81s go into 169. There's 2 of them with 7 left over. So that's 2 and 7 over 81 plus the 3, which would be 5 and 7 over 81. So I've got my value for x, 1 and 4 over 9. I've got my value for y, 5 and 7 over 81. Let's make our answer clear. And then let's check our answer using the other original equation. I've already used equation 1, so let's use equation 2. You're probably going to want to use a calculator for this, and I would recommend simply working out the right-hand side and seeing if it's equal to the left-hand side. Go ahead and give that a try. If you struggle with using mixed numbers, remember what the top-heavy fractions were for these. So if that's worked out, if you haven't already, make sure you go back, copy that example along with the steps, and let's move on to a more challenging question now. Once again, I've got two equations and they're both quadratics. They will both be parabolic curves. But this time I've got one positive parabola and one negative parabola. Can you tell which one's the negative one? Should be this one here because it's got the negative x squared term. So that means that this is the positive parabola. And you should notice something about parabolas is that their y-intercept is where x is equal to 0. So if that's 0 and that's 0, the y-intercept would be negative 7. So here this must be negative 7. And for the red curve, if x is equal to 0, those will both be equal to 0, y would be equal to 0, and see my red curve crosses at 0. Looking at this graph, you should notice that there are two solutions to these simultaneous equations. This blue curve crosses the red curve in two places. One's here and one's here. Again, we're not going to graph in order to solve this equation. However, knowing that there's two solutions helps you to know that you're going to have to solve a non-linear equation. We're going to solve a quadratic this time. So again, have a look at the description box below if you're not confident about solving quadratics. In this particular case, it would be helpful if you knew the quadratic formula. Still, we're going to start in the same way as always. We do have these two equations in the format where y is the subject in both cases. So I can set these equations equal to each other. So let's rearrange those to solve it. It looks like it's a quadratic, so let's definitely get the x squared terms together. And when I took the negative x squared from this side over to this side, it became positive x squared. And x squared plus x squared, that gives me 2x squared. It's not canceling out my x squared term. So I'm going to have a quadratic to solve here. So it's a good thing I brought my 3x over as well. My positive 3x became a negative 3x, because to solve a quadratic, you must know that that quadratic first needs to be equal to 0. So I've taken everything from the left-hand side over to the right-hand side, leaving 0 on the left-hand side. So x squared plus x squared is 2x squared. X minus 3x is negative 2x, and then minus 7. So 0 is equal to 2x squared minus 2x minus 7. I've got a quadratic that needs solving. I could try and factorize, but as there's a number in front of the x squared term, which I cannot factor out, I can't divide all three terms by 2. That would at least involve splitting the middle term, and I don't think I'm going to be able to do that in any easy way. So I'm not going to factorize this. I'm just going to go ahead and try and use the formula. You should be familiar with the quadratic formula. If not, again, check the description box below, because I'm not going to get into it too much. But for the quadratic formula, you always need to start by having your quadratic equal to 0 and have three terms in order: the x squared term, the x term, and the number term, so you can clearly identify what a, b, and c are for a quadratic formula. A is a number with the x squared, so 2. B is the number with the x term, so negative 2. And c is the number that's on its own, so negative 7. And make sure you've got the correct signs for your variables a, b, and c. Substituting that into the formula, we've got x is equal to negative b, so negative of negative 2. Put both negatives there. We know it's going to cancel to make a positive, but make sure you put them both there. Plus or minus the square root, and make sure your square root sign covers all of these terms. And b squared, make sure you put this in brackets, because negative 2 squared should be positive 4. A negative times a negative becomes positive. If you don't put those brackets, you're likely to end up with a mistake. Minus 4 times 2 times negative 7. Now I know that this is going to work out to be some positive value, so I'm not going to be square rooting a negative. I shouldn't have any math errors here. But if you have problems with your brackets, or you haven't put the correct signs on things, you may run into problems. That's a long formula, so don't forget the whole thing needs to be written over to a, so 2 times 2. You can put that directly into your calculator, but you do get a mark on the exam for showing that you can correctly substitute into the formula. So definitely write at least this step down. Now I've simplified this to this format, but it can be simplified a bit further. The square root of 60, if you've done any work with surds, simplifies to be the square root of 4 times 15, or 2 times the square root of 15. So this can simplify even further to 1 plus or minus the square root of 15 over 2. Now that is in simplified surd term. That's still exact, but if I want to find my two values for x, I do actually need to calculate this out to find one answer when I'm adding the square root 15 and one answer when I'm subtracting the square root 15. So my two rounded answers are 2.44 and negative 1.44. So I've got two possible values for x, and both of those values were rounded to the 3 significant figures, as it's generally asked on an exam. So step 2, we're done. Step 3, once you know the value of one of the variables, use either of the original equations to work out the value of the other variable. Now I'm looking at my two equations, and they're both quadratics, but I think you'll agree with me that equation 1, since it's only got 2 terms, might be a bit simpler than equation 2. So I've substituted my first value for x, 2.44, into equation 1. So 3 times 2.44 minus 2.44 squared, approximately 1.37. Again, this is rounded to 3 significant figures. And remember that if you've already used a rounded value like 2.44, your answer is becoming even more inaccurate because you've already rounded once. So try to avoid rounding errors. Try to work with exact values as much as possible. That's only one of my y values, because remember I've got two x values, so I should have two y values to go along with them. So again in equation 1, if x is equal to negative 1.44, y is equal to 3 times negative 1.44 minus, in brackets here, negative 1.44 squared. Those brackets are important because I know that any value squared, whether it's positive or negative, will become positive. Positive times positive is positive, and negative times negative is positive. So this gives me negative 6.40. Again, that's been rounded to 3 significant figures. I've written the 0 to make it clear that I did look at 3 possible digits, but that last significant figure happens to be a 0. If they ask for your answer to 3 significant figures, make sure you show 3 digits, even if one of them happens to be a 0. So I've got my x values, I've got my y values. Step 4, let's make that clear. When x is equal to 2.44, y is equal to 1.37. When x is equal to negative 1.44, y is equal to negative 6.40. If we were asked to show this on a graph, we would say that this was one of our coordinates where the two curves cross, 2.44, comma, 1.37, and this is another coordinate where our two graphs cross, negative 1.44, comma, negative 6.40. Step 5, let's check that our answers are correct. And this does get a bit confusing, but using equation number 2, let's substitute our values for x in there and see if we get the answers for y. So when x is equal to 2.44, y is equal to 1.39. Now I'm not going to panic about that because, as I said before, anytime we use rounded values, our answer is not perfectly accurate. That's not too bad, but let me just check if it works when x is equal to negative 1.44. So again in equation 2, if x is equal to negative 1.44, in brackets negative 1.44 squared plus negative 1.44 minus 7 gives me approximately negative 6.40. So that's bang on my answer from above. Again, both answers are rounded, but I have the correct answer there. So I'm fairly confident that my answers are correct. Although they are not perfectly accurate, I could say that my answers are correct to 1 decimal place or 2 significant figures. So I'm happy with that. Again, if you haven't yet done so, you may want to go back, copy that example as well as the steps before we go on to the practice exercise. Here you've got 16 questions to work out. However, only some of them can actually be solved using the equating method that I showed you today. Which of these can be solved by the equating method? Feel free to hit pause and take a minute to look at them carefully for yourself, and I'll show you in a minute. Have you figured it out yet? We can't use the equating method to solve these ones, but I'll show you in another lesson of how we could do that. We can, however, use the equating method to solve simultaneous equation questions in rows A and C. You may be thinking that some of these equations are not in the format where y is the subject. However, you need to be able to make y the subject of those equations. Feel free to hit pause now if you want to try and do that for yourself. If not, I'll show you how to do that right now, and then I'll leave you with these simultaneous equations to solve. Question 1 is already in the correct format. Question 2, the second equation, could be written with y as the subject if we just move that 3x to the other side. Question 3 is already in the format with y as the subject. Question 4, that first equation needs the y on its own, so let's move that 7x. For row C, question 1 is already in the format where y is the subject. However, in the first equation, you're going to want to expand that out. So write that as y equals x plus 1 times x plus 1, and expand those brackets out into their 3-term quadratic form. Question 2 is already in the format where y is the subject. Question 3, we can get to that format simply getting y on its own. For that first equation, move the x to the other side, so 11 minus x. And for the second equation, move the x to the other side, so 30 over x divided by x, a reciprocal. For question 4, again, let's get that y on its own. Move the x to the other side, again, a reciprocal. And for our second equation, just move the 2x to the other side. Now you have 8 simultaneous equations to be solved. They're all in the format where y is the subject, so go ahead and equate them. Solve the equation that you've got. Substitute your answer into one of the 2 equations to find your other variable value. And check your answer at the end to make sure it works in both equations. Go ahead and hit pause now so that you can do that, and the answers will come up in just a minute. I hope you had a chance to hit pause because here come your answers. For question 1, when x is equal to 1, y is equal to 1, and when x is equal to 10, y is equal to 100. Question 2 has got 2 solutions as well. 3, 4, C1, C2, C3, and C4. Now, how did you do? I hope that you noticed that with your reciprocals, you can always get rid of these fractions by taking the denominator to the other side and multiplying. And that's how we ended up with quadratics again to solve, which explains your 2 answers. And of course, quadratics don't always have 2 answers. Sometimes it has the same answer repeated. Hopefully that went fairly well. If you need any help or you have any doubts, please leave me a comment in the comment section down below. But please don't get discouraged. This is challenging. It does take a lot of algebraic skills, particularly when we're dealing with these quadratics. So till next time, keep at it, keep practicing, and I'll see you soon.